In this video, we're going to look at rolling motion and learn how to apply conservation of energy and Newton's laws of motion to problems involving disks or balls or objects rolling down inclines. In this class so far, we've looked at two types of motion. There's pure rotational motion, where the center of mass stays put, but an object rotates around its center of mass. And there's translational motion, where the center of mass moves and every point in the object moves along with that center of mass. It does not rotate around the center of mass, but just moves purely translationally. Well, we can combine rotation and translation together to get rolling motion. Rolling motion is a combination of rotation and translation. The center of mass moves and the object rolls around that center of mass. So what I want to do is look at a special type of rolling motion called rolling without slipping. That's what happens, for example, when static friction is acting between a tire and the road. So let's think about what happens if a wheel rolls along the ground without slipping. So let's say this wheel here is rotating with some angular velocity omega, and at the same time its center of mass is moving at v center of mass. And this wheel has a radius r. Okay. Well, if it's rolling without slipping, that means that this point never loses contact. That is, it doesn't slip. It just touches the ground and then lifts off as this wheel goes around. So that means that this point here is in contact, and then sometime later the wheel rolls down, and this point here is in contact, and then the wheel rolls down, and this point here is in contact, and so on. The wheel is rolling until the wheel goes through one full rotation. That is, it's rotated. This point at the bottom of the wheel here has gone all the way around, come all the way around, and ended up back where we started. So the angular displacement of the wheel, delta theta, equals 2 pi. It's gone around one full revolution. At the same time, all the points on the wheel have to have touched the ground. So this delta x, this distance of the center of mass of the wheel moved, has to be the same as the circumference of the wheel. That is, delta x has to equal delta theta times r, which is 2 pi r, the circumference of the wheel. If this point went all the way around and every point in between touched the ground, well, the length of all the points in between is 2 pi r. So delta x equals 2 pi r. So in general, we get this relationship. Delta x, the displacement of the center of mass of the wheel, equals the angular displacement, delta theta, times r, the radius of the wheel. So now what I can do is just go ahead and divide both sides of this by a time interval, delta t. That is, this is the amount of time it takes for the wheel to roll through this distance, delta x. Well, delta x over delta t, that's just the velocity of the center of mass. Delta theta over delta t, that's just the angular velocity omega. So I get this relationship here. The velocity of the center of mass just equals the angular velocity omega times the radius of the wheel. I can take the derivative of both sides of this equation to get another relationship, which is that the acceleration of the center of mass equals alpha times the radius of the wheel. So for a wheel rolling along the ground without slipping, I can use these two relationships. I can always say that the acceleration is equal to the angular acceleration times r, and the velocity is equal to the angular velocity times r. If the real wheel is slipping while it's rolling, these relationships are no longer necessarily true. I cannot use them in problem solving. I can only use these if the wheel is rolling, or any round object is rolling without slipping. First, let's examine the problem of a ball rolling down an incline. So we have a ball of mass m and radius r, and it starts from rest at a height of 2 meters and rolls without slipping down a 30-degree slope. We want to find the linear acceleration of the ball And we want to find the linear velocity of the ball when it hits the bottom of the ramp. So here's how we're going to approach this problem. For part A, we're going to use Newton's second law. That is, where you're going to use a combination of F equals ma and torque equals I alpha. For part B, we're going to use conservation of energy. That is, we're going to say that delta K plus delta U equals 0 and use that to find the final velocity. So let's go ahead and start out with part A first. Okay. Well, what we're going to do is draw first a free body diagram for this ball. So here is our ball. It has a weight force, mg, pointing down. There is a normal force, n, that points perpendicular to this incline. And finally, there is a static friction force between the ball and the incline. If there were no friction, the ball would just slide down the incline. It wouldn't roll at all. If this were kinetic friction, that would mean the ball was slipping. So in order for the ball to roll without slipping, this must be a static friction force. And for this problem, we're going to use our tilted coordinate system. Our coordinates are going to look like this. Here is x, and there's y. So let's go ahead and write out Newton's second law in the x and y directions. X, y. So in the x direction, we have F net x equals max. In the y direction, we have F net y equals may. We know that ay is going to be 0. This ball isn't going to fly up into the air or out of the air. We know this ball is going to accelerate down the incline with some acceleration a, which points in the x direction. So we'll say a equals the magnitude of a, I hat. So in the x direction here, we have, well, the x component of mg. We've done this problem enough times that we know this is just mg sine theta minus the static friction force is equals ma. And in the y direction, we have the normal force n minus mg cos theta equals 0. Okay, so you might say, well, let's go ahead and solve for n, and then we can plug that in for the static friction force. We can say static friction is mu s times n, and we can solve for this acceleration. Except that doesn't actually work. We don't know that this static friction force equals mu s times n. We know that the static friction force is less than or equal to mu s times n. But we can't just say that it is equal to it. We don't have enough information to solve for the static friction force. So right now we have this one equation here and two unknowns. We don't know Fs and we don't know A. So the way we're going to do this is actually we're going to completely ignore our y equation. Our y equation doesn't do anything. Doesn't matter. We don't need it. Instead, we're going to write down Newton's second law in angular form. We're going to write down torque equals I alpha. So we know that the net torque equals I alpha. We know that this wheel is going to rotate clockwise like that as it rolls down the incline if it's rolling without slipping. So I don't need to worry about the vector direction of this torque or angular acceleration. We just know that it's going to roll this way. So we can look at all of our forces and see what torque they contribute. Our center of rotation is going to be right here in the center of the ball. And our ball has a radius r that points from the center to the places where these forces act. This is our vector r. So let's go through each of these three forces and see what the torque is. Let's first look at the torque from the normal force. So the torque from the normal force we can write as the normal force N times R which is the distance away from the center of mass that this normal force acts, times sine theta. Okay, well, really this normal force acts between the incline and the ball, so the point of contact is down here, a radius r from the ball, but the vector that points from the center of rotation to that point where the normal force acts is this vector r, and the angle between r and n is 180 degrees. So this equals n times r times sine of 180 degrees, but sine of 180 degrees is just 0. So the torque from this normal force just equals 0. Okay, so the normal force does not apply any torque. We can see that just sort of easily by seeing that this normal force vector points straight through the center of rotation of the ball. So it can't apply any torque. It's not going to rotate the ball around the center of rotation because it points straight through the center of rotation. Let's look at the torque from mg. Well, this equals mg times r times sine theta. Now, this mg acts right at the center of rotation. We know that when we're calculating torque, we can treat the weight force as if it acts right at the center of rotation of the ball. So, r now equals 0, which means this torque also equals 0. So gravity does not apply any torque. The only force that's applying torque to this ball is the static friction force. The torque from this static friction force, tau Fs, equals, well, it's going to equal this static friction force, Fs, times the radius r of the ball. That's how far away Fs acts from the center of the ball. It acts right at the point of contact. And then times the sine of 90 degrees. The static friction force makes a 90-degree angle with the radial vector. The radial vector points along the radius of the ball. The static friction force points tangentially to the ball because it's acting between the ball and the surface of the ramp. So this sine of 90 degrees just goes to 1, and we get this really simple answer that this torque from friction just equals the static friction force times r. Okay, so we can go put that into our equation, that the net torque is the static friction force times the radius of the ball. This equals the moment of inertia of the ball, I, times the angular acceleration, alpha. Okay, now we have two equations, but we have three unknowns. We don't know Fs, we don't know A, we don't know alpha. So we need one more equation linking these variables together in order to solve this system of equations. Well, remember, the rolling without slipping condition says that the acceleration of the center of mass of the ball, which is A, has to equal the angular acceleration alpha times the radius of the ball r. So that's our last equation here that allows us to solve this problem. We want to find A, so what I'm going to do is go ahead and write this as alpha equals A over r. And then we can write this torque equation as Fs times r equals I A over r. Can solve this for Fs. Fs equals I A over r squared. And then I will plug this in up here for Fs. When I do that, I get mg sine theta minus I A over r squared equals ma. I can solve this for A, and I get that the acceleration of this ball, well, A times m plus I over r squared equals mg sine theta. So A equals mg sine theta over m plus I over r squared. So this equation, I'm going to put a dashed box around it because this is true. This is the acceleration of any object rolling down an incline without slipping. just mg sine theta divided by m plus the moment of inertia I divided by r squared. But we still have to figure out what this moment of inertia is. Well, let's say this is a solid ball. So we can go to our list of moments of inertia, and we find that the moment of inertia of a ball, which is really the moment of inertia of a solid sphere, is 2/5 m r squared. So I can go ahead and plug that into this equation for A, and I get that the acceleration A equals mg sine theta over m plus 2/5 m r squared divided by r squared. Well, look, these r squareds just cancel out. And then once those r squareds cancel out, I also see this m cancels out. I just get that this acceleration equals g sine theta over 1 plus 2/5. 1 plus 2/5, that's 7/5. So I can finally just write this as 5/7 times g sine theta. Okay, so this is pretty interesting. The moment of inertia of any round object rolling down an incline is going to be some multiple of mr squared. So the acceleration of any object rolling down an incline is just going to be g sine theta, which is what we would get if it were sliding without friction, times some fraction. In this case, that fraction is 5/7. And that fraction does not depend on m or r. It only depends on the geometry, that is the shape of the object. So you'll get one fraction for a solid sphere, a different fraction for a hollow sphere, a different fraction for a ring, and so on. So this is how you set up Newton's second laws to find the acceleration of an object rolling down an incline. Okay, now let's do this using conservation of energy. Well, remember our free body diagram for the ball. I'll just redraw it. There is mg pointing down. There is the normal force N pointing like that. And there is a static friction force acting on the ball. Okay, so we can use the work-energy theorem, which says that the work done by external forces on this ball equals the change in kinetic energy plus the change in potential energy plus the change in thermal energy. Okay, well, normal force doesn't do any work, so we don't have to worry about the normal force. mg acts as a source of potential energy, and the static friction force, well, it doesn't do work because it's not actually moving the ball. The point where the static friction force acts on the ball is that point of contact is always stationary. So the static friction force isn't actually pushing the ball, and it also doesn't contribute any thermal energy, because only kinetic friction contributes thermal energy. It's the rubbing, the slipping, that causes thermal energy to increase, not just any static friction force. So we can just say that mechanical energy is conserved. That is, 0 equals delta K plus delta U. Or we can write this as K final plus U final equals K initial plus U initial. All right. So, well, let's say the ball rolls down this 2-meter incline. So U final is going to be 0. And U initial will be mg times h. We'll call 2 meters h. And K final is going to be 1/2 mv final squared. But there's also going to be a rotational kinetic energy. We have to include that 1/2 I omega final squared. So for a ball rolling without slipping down an incline, we have to include both the translational kinetic energy, 1/2 mv squared, and the rotational kinetic energy, 1/2 I omega squared. K initial is 0. It starts from rest, so this just equals mgh. All right. Well, now once again, I've got one equation and two unknowns, but my rolling without slipping condition says that omega equals the velocity v divided by r, the radius of the ball. That's my rolling without slipping condition. So I can write this as 1/2 m v final squared plus 1/2 I times v final over r squared equals mgh. I can go ahead and solve this for v final. I get v final is going to equal 2 mgh over m plus I over r squared square rooted. I just factored out a v final squared divided by everything else and then took the square root. But I can go one step further. I can plug in this expression for the moment of inertia of the ball. And I get that this equals the square root of 2 mgh divided by m plus 2/5 m r squared over r squared. Once again, r squareds cancel out. And then the m's cancel out. And I get something a lot like what I got before. This time I get v final equals 5. Let's write this all out. This equals 2gh divided by 1 plus 2/5, which is 7/5, all square rooted. This I can simplify to be the square root of 10/7 times gh. So once again, if this ball were just a mass sliding down the incline without friction, the answer would be square root of 2gh. So I take that answer and multiply it by some fraction that depends on the geometry of the rolling object. In this case, it has to do with this fraction 2/5 here. And I end up getting square root of 10 over 7 times gh. If I plug in my numbers here, I get this is the square root of 10 over 7 times 9.8 meters per second squared times the height, which is 2 meters. And this gives me 5.3 meters per second. So I've shown you how to solve this problem of a ball rolling down an incline with conservation of energy and with Newton's second law in order to find the acceleration. Here's a conceptual question. Which arrives at the bottom of an incline first? A ball, a disc, or a hoop? Assume that each object is released from rest to the top of its incline and that they all have the same mass and radius. Okay, I've given you the moment of inertia for each of these objects here. So go ahead and think about what your answer is. Does the ball, the disc, the hoop reach the bottom first, or does it depend on the angle of the incline? Pause the video, think about it for a minute, and come back when you think you have an answer. Alright, well I'll give you a hint. It doesn't depend on the angle of the incline. And it's not the disc. It's either the ball or the hoop. It's either the one with the smallest moment of inertia, which is the ball, or the one with the biggest moment of inertia, which is the hoop. So take a minute, think about what your answer is, pause the video, and come back when you know what it is. Alright, well here, the correct answer is the ball reaches the bottom of the incline first. And the reason for that is it has the smallest moment of inertia. If I look at this equation I wrote here for v final, the bigger this moment of inertia is, the smaller the final velocity is. So the slower it's going to be going when it reaches the bottom of the incline. So, therefore, if we want something to go fast, we want to make its moment of inertia divided by its radius squared as small as possible. That is, we want to make this fraction, which for the ball is 2/5, the disc is 1/2, and the hoop is just 1. We want to make that fraction as small as possible. The smaller that fraction is, the faster we're going to be rolling when we reach the bottom of the incline. If we were in class, I would do a demonstration of this for you right now, but just trust me, this ball is going to reach the bottom of the incline first. let's do one last example, and I want you to see if you can figure this one out on your own. So a wheel is a uniform disk of mass m and radius r. A horizontal force F is applied to a massless axle that runs through the center of mass of the wheel. So there's some axle here with no mass that runs right through the center of mass, and that's what we apply this force F to. If the wheel rolls without slipping, what is the linear acceleration of the wheel? So first thing I want you to do is try drawing a free body diagram for this. So go ahead, try to draw the free body diagram, pause the video, and come back when you think you have it drawn. Okay, well, first, there's a normal force acting between this wheel and the ground. That normal force is going to point up like this. Normal force N. There is, of course, a gravitational force mg that points down like that. Forgot to put this as a vector. And then, if this wheel rolls without slipping, there has to be a static friction force between the wheel and the ground. Static friction force points like that. Okay, so those are your other forces other than this force F that are acting on this wheel. So now that we have the free body diagram drawn, see if you can write out Newton's second law in the x, y, and angular directions. So pause the video, try to write out Newton's second law for each direction, and then come back and compare to what I have. Okay, so in the x direction, we have F minus the static friction force equals m times a. We know that this wheel is going to accelerate in this positive x direction like that. In the y direction, we have n minus mg equals 0. And in the theta direction, well, the only one of these forces that exerts any kind of torque is the static friction force, for the same reason that we discussed with the ball rolling down the incline. So our only torque is Fs times r, the radius of this wheel. This equals I times alpha. Okay, so with these x, y, and theta forms of Newton's second law, we can basically ignore the y direction. It doesn't matter here. All we need is x and theta. What we want to do is solve for the acceleration a. So, once again, pause the video, see if you can solve for a, and come back when you think you have an answer. Well, the key to solving for the acceleration of the wheel is that we need to know that this wheel has an angular acceleration like that, and that the relationship, because it is rolling without slipping, is alpha equals a over r. Or I should write this as capital R here. Okay, so we have Fs times r equals I a over r. That means that Fs equals I a over r squared. I can plug that in just like we did with the wheel rolling down the incline. Plug that in up here. I'll bring this equation down so we have some more room. I get F minus I a over r squared equals ma. Solve this for a. I get ma plus I over r squared times a equals f. And I can solve this. I can factor out this a and divide by all that other stuff. I get a equals f over m plus I over r squared. All right, my last step is I know that this is a uniform disk. I can look at my formula for the moment of inertia of a uniform disk. It is 1/2 m r squared. Plug that in here, I get this equals f over m plus 1/2 m r squared over r squared. Sorry, this should be a capital R here. These r squareds cancel out, and I get f over m plus 1/2 m. So me a, not alpha, a equals the force over 3/2 mass. I'll write this as 2/3 f over m. Okay, that's our acceleration in terms of these quantities, f and the mass m of the wheel. So think about what this means. If this were not a wheel, but rather a mass sliding without friction, well, then the acceleration will just be F over m. Since we have friction here, and this is a uniform disk, that just rescales that acceleration. It still doesn't depend on the radius of the wheel, but now this acceleration is just going to be 2/3 F over m. So just like in the last problem, where we ended up multiplying our answer for sliding without friction by some fraction, we multiply our answer for sliding without friction, which is F over m, by the fraction 2/3. Okay, that's all I'm going to say about rolling without slipping. You'll have plenty of homework problems where you'll practice this, and I think it's one of the more fun things that we do in this class. So I'll definitely be giving you a problem on your last exam involving something rolling without slipping.